Hello guys, welcome to Yebo Physics on a Thursday afternoon. I hope I find you well and I hope you are coping up well with your studies. Welcome to yet another Yebo Physics tutorial session where we are going to be solving physics problems together. I hope these tutorials are adding to your understanding, and I hope that you will greatly benefit if you diligently follow through. Feel free to interact with me via the chat box, or if you are joining live on Teams, also feel free to unmute your mic and interact with me. It will be a pleasure to get feedback from you as the chat session is going on. So what are we looking at today? Today we want to do a quick revision on Newton's laws of, on calculations involving Newton's laws of motion, which is the second law in particular. We are going to be looking at a problem on a slope, and thereafter we're going to jump and look at questions on work energy, right? Work and energy. That is for the PHYV 101 group. So that is what we intend to look at this afternoon. If you have any questions, please do let me know, or let any one of the tutors know, so that you may get the help that you need. Alright, so let's get started. If you have not managed to join in live, I hope that you will go through this video later on to check on the specific questions that you may need help on. So we're going to be looking at questions 9 to 11. We're going to be looking at questions 9 to 11 on the PHYV 101 questions. And if you have missed any of the previous tutorial sessions, please do check for the live recorded, or for the recorded sessions on YouTube, to get the specific question that you may have missed. Okay, so let's get started. We are going to start with the questions that we have here for the FVV 101 group, right? But this is still physics, even for the PHYV 101 group. But this can also still be useful, and it can add to your learning and add to your understanding. Alright, so you can follow through as well while we are working on these problems. So question 9 says, for 3 situations, so it's question 9 on both sides. But we're going to be starting with the questions that are on the right of the screen, the right hand side of the screen. So this is where we are. I'm just going to highlight the question that we're doing, question 9. It says, for 3 situations described below, use the lesser than sign, greater than sign, or equal symbols to complete the statements for an object at rest. So we have got an object that is on a slope. We've got an object that is on a slope there, and we are supposed to analyze the forces that are going to be acting on that object, right? And I think you have been doing a number of such problems by now. You should be comfortable with the problems which involves objects placed on an inclined plane. Okay, so if the object is at rest, the weight down the slope, or the weight, or the component of the weight parallel to the slope, how is it going to be compared to the frictional force? So if the object is at rest, it means there is no motion. The resultant force is 0, both in the x and in the y axis. And the forces acting on the x-axis are the component of the weight down the slope, which is this one, and the friction. So for the object to be at rest, it means that the summation of forces in the x is equals to a 0. And if they are equal to a 0, it means that the force of friction is equal to the component of the weight down the slope. So it means that these two are equal. That's what it means, okay? We've just explained that. Then what about the component of the weight? The component of the weight perpendicular to the slope, which is this one, and the normal force. Again, this object is at rest, it's not moving, neither is it moving in the y nor in the x. So it means that these two forces again are equal. Now we're told that the object moves at a constant speed. If the object moves at a constant speed, how does the weight down the slope compare to the frictional force? So this object is now moving, so this is no longer static friction, this is now kinetic friction in play, okay? So the question also mentioned that indicates whether it's a static or a kinetic. So this is F kinetic and this was the static friction. So what can we say? It's moving at a constant speed, which means that the acceleration is equals to 0, which means that the summation of forces in the x is equals to a 0. Remember, Newton's second law of motion stands for to every accelerating body there is a resultant force. So this body is not accelerating, it's moving at a constant speed. So what that means is that the summation of forces in that axis should be 0. That makes this these two equal. Alright, and the normal force and the component of the weight perpendicular to the slope, this object is moving down the slope, it's not moving in the y direction, so these two remain equal because there is no force that is there is no motion in the y direction. Okay, then what else? Object accelerated down the slope. So if the object is accelerating down the slope, now we have acceleration. If we have acceleration, it means that there is a resultant force in the x direction. And if it's moving down the slope, which means the component of the weight must be greater than the frictional force, or the kinetic frictional force, so that this block slides down, okay? So this is Fk. Again, we're not told of any motion in the vertical direction, and what that means is the component of the weight perpendicular to the slope remain equal to the contact force. So this is important when analyzing a situation where we have got an object that is on a slope. Alright, this should be just some kind of revision, and I am sure that this is not much of a problem to you guys. So let's look at the next question. Question 10. It says a 40 kg box slides down an inclined plane, at 30 degrees at a constant speed, okay, of 21 meters per second. So if the speed is constant, which means acceleration is equals to 0, which means the summation of forces in the x should be 0. Again, it's Newton's second law of motion coming into play. Alright, so if it's moving down the slope, it means that the component of the weight should be greater than the frictional force. Right? That is what we observed earlier on. Right? If the component is sliding down, it means the weight down the slope, or the component of the weight down the slope, is greater than the frictional force. Is it? Oh, they are equal because it's not accelerating. Wow, it's not accelerating. I just said here that the summation of forces in the x is 0, so they are equal. Actually, they are equal because it's moving at a constant speed. It's not accelerating like the case in the previous question. So it's not accelerating, it's constant, so summation of forces is 0. Okay, so we've analyzed that these two forces are going to be equal. So we're told that the box is 40 kg, so the weight there is going to be 40 times 9.8. Newtons, right? That's the weight. And the component of the weight, which is this one, perpendicular to the slope, we know that it is equals to mg cos theta. So in this case, it is going to be 40 times 9.81. That is our mg cos 30. You will punch that, okay? And we've obtained this one. And the weight down the slope is mg sine theta, so this will be 40 times 9.81 cos 30, sine, the component of the weight down the slope, sine the angle, sine 30. And this is in newtons. So what is going to be the contact force? Contact force, what then becomes our contact force? Our contact force, again, we do not have a force that is acting in the, we do not have a resultant force in the vertical direction, so which means the contact force is going to be equals to this magnitude. So it's also going to be 40 times 9.81 cos 30. Alright. Then we said that the summation of forces in the x is equals to a 0, which means that the frictional force is equals to 40.9.81 sine 30. So with this we would have completed our equation. So we are being asked the net force down the hill. We've already analyzed and said the summation of forces is 0, so it's going to be 0 Newton. And if the force is 0, we don't expect any acceleration according to Newton's law of motion. Right, so that is the case in this particular question. So you see, it's quite similar to the previous question that we looked at. Now coming to question 11. Question 11 says an object, so a force of 300 newtons is placed or is applied as shown. So this is our force there, as shown to a 65 kilogram object originally at rest on an inclined plane. So it was originally at rest, which means initially u was equal to 0 at 28 degrees. So this is 28 degrees. Assume a constant friction. Fill in the blanks. Right, so we should fill in the blanks. Right, so what do we have there? So we have got that force that is being applied, a force of 300 newtons. So ideally that force has got a component in the x and it has got a component in the y. And in this case, see that we should fill in for the frictional force, we should fill in for the component of the weight down the slope. Component of the weight down the slope shouldn't be a problem. Why? Because we've done this one before. W equals to mg sine 30. And what is our mass? It's, oh, why am I putting 30? That's from the previous question, sine 28. And this is going to be 65.9.81 sine 28. Same goes with the component of the weight down the slope, which is going to be equals to mg cos 28, and that will be 65.9.81 cos 28. Alright, so our weight is 65 times, our weight is 65 times 9.81. Okay, then we can batch that. What else can we easily complete? We have actually completed the component of the weight down the slope. We've completed for for the weight down the slope. Also completed for the weight perpendicular and the actual weight. Now let's look for the frictional force, the normal force, I think that is what is missing, and the component of the weight down the slope we have it. So there's important information that we've been given, and this important information tells us that assume a constant friction. So assume a constant friction. Object is initially at rest. Okay, right. So what does that mean? If the object was originally at rest, when the object was originally at rest, it means that the component of the weight down the slope was equal to the frictional force. Okay, which is what we did earlier on to say if an object is on a slope and there is no other force being applied and that object is stationary, it means that the component of the weight down the slope is equal to the frictional force. Alright, so which means our frictional force is equals to 9.81 sine 28. So these two are equal. So probably we can put the calculations. So that's 65. That's 65 times 9.81 sine 28. So we get 299.36. 299.36 newtons, which is the same as 299.36 newtons. So this one we've completed, this one we've completed, and the component of the weight down the slope, and this we've completed, and this we've completed. Let's just punch 65 cos 28. 563. That's 563.01 newtons. So that is completed as well. So this was our static friction. But we're given a hint that assume the friction remains constant, which means our static friction is equal to the kinetic friction. So Fk is equals to 299.36, because now we want to analyze for a case when this object is now moving down the slope. The friction will still remain the same. That is what we have been told in the question. Alright, so now let's analyze when the force is applied. So when the force is applied, this object now begins to move, which means that this object is going to then accelerate because of the force that is now being applied. So you can satisfy yourself that this is our angle theta there, and we will have a right angle triangle there. And on that right angle triangle, we need to find the x direction of this force, or resolve it in the x. Alright? And when we resolve that angle at an x, the component of the weight, the component of the 300 Newton force has to be resolved down the slope. That would be 300 sine 28. You should be familiar with the resolving now. So you can resolve by choosing any right angle triangle with the appropriate angle. And in this case, we'll use that angle theta, which is 28. So let's look at the summation of forces in the x. Summation of forces in the x should be equals to ma, which is the acceleration in the x. So how many forces do we have? We have the frictional force, which is acting in the negative axis, so it's going to be negative F, which is the frictional force, right? And this is our kinetic friction, right? So this is the only force that is acting in the negative direction. Which other forces do we have? We have the mg down the slope, and we have the 300 sine 28, which is the component of that force down the slope. Okay, it's just the same as the component of weight down the slope. It's mg sine 28. So here we've got a force that is being applied, and when we resolve that force, it becomes 300 sine 28. Alright, so that is in the x direction. Okay, so we are going to add plus the component of the weight down the slope plus the force in the 300 F 300 in the x is equals to ma. Okay, now what do we do next? So that is equals to ma. So what we can find is the net force of these three forces, because we are being asked to find the net force. Okay, before we use our Newton's second law of motion, we can actually find the net force. All right, so F net is equals to negative Fk plus W parallel plus F, which is the 300 force in the x direction. Right, so let's substitute our Fk. So the component of the weight down the slope and the kinetic friction, we realize that they are the same. the component of the weight. So I'm going to highlight this again. The component of the weight down the slope and the frictional force, we said they are equal, and in this case they said the frictional force remains constant, which means this is also equals to Fk, the kinetic friction, which means this weight down the slope is also equal, it is also equal to the kinetic friction. So these two are equal and opposite, which means that these will cancel out. Alright? These two will cancel out because they are equal. We just showed this frictional force, you can put a negative sign, and this one is positive. So this will be a 0 plus 300 sine 28, which is the weight that has been applied, and we have resolved it in the x direction, which is the component, which is in the same direction as the component of the weight down the slope. The component of the weight down the slope, we say it's mg sine theta. So it's the same case with the force that is being applied when we need to resolve it down the slope. It will be that force multiplied by sine theta. So that becomes 300 sine 28. So we need to punch that. Sine 28, we get 114. So you can see that from the screen. 140.84 newtons. So that's what we get. Then getting acceleration shouldn't be a problem. Our F net is equals to ma. So our F net becomes 140.84 equals to our mass 65. So our A will then become our answer divided by 65, 2.16, right? 2.17 if you round off, 2.17 meters per second squared. So that is how we have calculated our acceleration and the net force down the hill. Alright, so I don't see any questions, I don't see any chats on YouTube, neither do I see any chats or comments on the YouTube channel so far. I believe that you are following quite well. I believe that you're following quite well. Alright, so what's next? We have got another question that we have here. So I'm just going to erase this. Right, so let's move on. I was just checking for questions on the chat. I don't see any at this moment. So it says calculate the tension in a vertical strand of spider web if a spider of mass 8 times 10 to the negative 5 kilograms hangs motionless on it. Okay, alright. So we've got a vertical strand of a spider web. So I'm going to illustrate this. So these are vertical strands, which is probably attached somewhere. Okay, and we have got our spider. Spider has got how many legs, by the way? 1, 2, 3, 4, 5, 6, 7, 8. I think it's 8. Could be 8, right? So there's a spider, and it's hanging there. And what else are we told? We have been asked to find the tension. Okay, calculate the tension. Alright. So let's identify the forces that are there. So of course we have got the component of the weight, mg, going down, and the tension will be the component, will be the force actually that is going to balance this this weight, alright? So it's going to be upward. So we've got our tension, and this spider is motionless, right? Motionless, it's not moving. So there's no any other forces that we can include there, since it's not moving, right? So we are interested in the y direction. We're interested in the y direction. There's nothing taking place in the x direction. So remember, summation of forces in the x is equals to ma. Is there any indication that this body is accelerating? We're told that it's stationary. So this should be equals to 0. And let's sum the forces that we have. We've got our tension going up and mg down in the negative. So this is going to be equals to 0. And what that means is the tension is equals to the weight. So what is the mass? 8 times 10 to the negative 5 times 9.81 kilograms. Let's calculate that. So we get 7.85 times 10 to the negative 4 newtons. So this becomes our answer. So our tension is equals to 7.85 times 10 to the negative 4 newtons. Alright, so that is how, so we in principle used our Newton's second law again to find the component of, the tension the tension. Okay. Let's move on to part B of that same question. It says calculate the tension in a horizontal strand of spider web if the same spider sits motionless in the middle of it. Okay. And the strand sets at an angle 12 degrees below the horizontal. Okay. So we have to sketch this problem. We have to sketch it. So I'm going to erase this link that you have understood this. So we can say initially what we had a wave like this, right? And the spider sits on it, and we're told that it's going to sag 12 degrees to the horizontal. So this is our horizontal. Is our 12 degrees. This is our 12 degrees. Alright. So you can put vertical. Axis like that. So which means our spider will now be here. This is our spider seated. Okay. And causing that sagging of the strand. Right, so let's identify the forces that are going to be acting there. We obviously have the component of the wave, the weight. And what else are we given? Oh, we're asked to find the tension. So our tension is still at the one supporting the weight. So it's in this direction. So this is our T tension. Right, because this is still the same one continuous strand, right? So the tension is going to be the same. Alright, so what do we need to do? So we can add the horizontal axis there. See, we have got a nice Z angle, suggesting that here as well is 12 degrees according to the Z angles. Alright. So, what are we told? Calculate the tension in the horizontal strand of spider web. If this is okay, so we want the tension in the string. So we can start by analyzing in the X. So F in the X. Summation of first in the X is equal to and the X, right? And this is stationary and it's going to be equals to 0 anyway, but we can identify the forces in the X. So we've got this force and this force, so you can actually use these right angle triangles to resolve T in the horizontal. do that, if you use this angle that I've just shown here, that should give you t cos 12, right? One of them is negative, so it's going to be t negative t cos 12 plus positive t cos 12 equals to 0. So there's nothing happening in the x direction, so there's no way we can find tension using in the horizontal motion rather. Okay, so now let's analyze the vertical. Let's analyze the vertical. So the summation of forces in the y, summation of forces in the y will be equal to what? Oh, okay, it will be equal to ma in the y, but again we're told that it's motionless, so this should be equals to 0. Now let's identify the forces that we have. We've got this tension, so these have to be resolved in the vertical. So we can use the right angle that we've shown and to resolve and find the y side. Okay, and that will give you what? T sine of 12. Because for the horizontal, that's what we got. And these two are all in the positive, but this one is in the negative. So it's going to be t sine 12 plus t sine 12 minus mg equals to 0. Okay, which means 2t sine 12 is equals to mg, and what that means is t, if you make t the subject, that's the next thing, t is going to be equals to mg over 2 sine 12. And let's substitute our mass. So our t is going to be equals to our mass. We're told is 8 times 10 to the negative 5 times 9.81 over 2 sine of 12 over 2 sine of 12. So we get, if we put that in standard form, that will be 1.89 times 10 to the negative 3 newtons. Right. That becomes our tension in this case. Oh, this is okay. So that is what we are working towards, right? All right. So I guess that should be fine with you guys. That should be fine with you guys. Right. So let's proceed. So these were the last questions that we had for the FVV 101 groups for today. This is what we were solving. Let's jump on to questions involving work energy for the PHYV 101 group, and we've got 3 questions, about 3 questions that we need to solve together. This one, this 2, there's another one there. Alright, so this will involve the principle of conservation of energy as well. If you missed any of the questions before these ones, please do check the recording. You should find the questions. Right. So we'll take a short break while I switch the screen to create a working space for the PHYV 101 group. Hello guys, welcome back. We had to take a short break while we were doing a screen switch over so we can solve together questions from the model side. That is question 9 to 11. All right. So if you're joining us for the PHY V11 group, this is going to be helpful for you. The FEV group, this is still going to be helpful because you are still also going to be doing the concept on work energy, right? So this will still add to your learning and to your understanding. All right. So let's tackle question 9. What does it say? So it says 2 clowns are launched from the same spring. The spring compressed with the spring compressed the same distance each time. Okay. Clown A has got a mass of 40 kilograms and clown B has got a mass of 60 kilograms. Determine the relation between their speeds at the time of launch. So let's analyze the information that we are given. So we're told that delta x for A is similar to delta x for B, and mass for A is equals to 40 kilogram, and the mass for B is equals to 60 kilograms. What else are we told? So which means that our delta XA is equals to delta XB, which is equals to our delta X anyway, because we're told that these two are the same. So what else, what other information do we have? Also I've asked to find their speeds, right? The relation between their speeds. So what do we do? So if we're analyzing this question, the spring is compressed, right? The spring is compressed, and it means we are going to have some elastic potential energy, which is the work done in loading that spring, right? And when what else are we told? Okay, so they are being launched from the same spring, so meaning that the energy that has been used to load this spring is going to be equal to the energy required to, it's going to be equal to the energy that these clowns are going to get as their kinetic energy. All right? The energy that they are going to get is as a result from the energy that was stored by the spring, which was used to load this spring. All right, so we have got we can say what, principle of conservation of energy. So the energy that was loaded onto the spring is being transferred to the kinetic energy of these clowns, right? So for A, so which means for A, what are we going to have? The kinetic, the work done in loading the spring, we know it's a half K, and we're told that the extension is the same, so it's going to be delta X squared equals to half mv squared, the kinetic energy, but this is half the mass, of A, right? So I have ma, and the speed va squared. Then for B, we're going to have half k delta x squared equals to half m b, right? vb squared. All right, so in both equations we see that we've got common terms. So we are told that we know that this is delta x and this is delta x. In both cases they are just the same, right? So we can see that these two sides are the same, so we can equate these two together, right? So this is our equation 1, this is our equation 2. So equation 1 is equals to our equation 2. So that then becomes to half MAV MAVA squared being equated to half MBVB squared, right? We can cancel these terms, all right, or multiply by 2 on both sides. And we want the relationship between A and B. So we can make A the subject. So VA squared is going to be equals to MB over MA times VB squared. So we can put a square root on both sides. So this will remain VA equals to the square root of MB over MA times VB. Now we can substitute VA is equals to the square root of mass of B, we're told it's 60 over 40 VB. And if we simplify this, this should be the square root of 3 over 2 VB. All right. So that should be the relation between those two. Let's see. Yes, we do have an option to start. That is indeed what we were supposed to get. So moving on to question 10. It says a 1 kg block is released from rest at the top of a frictionless inclined plane. And that makes an angle of 37 degrees with the horizontal. An unknown distance down the incline from the point of the release, there is a spring with a constant of 200 Newton per meter. It is observed that the mass is brought momentarily to rest after compressing the spring a distance of 0.2 meters. How far does the mass slide from the point of release until it is brought momentarily to rest? Okay. All right, so shall we continue? So we can start by sketching. Earlier on we did look at some problems of objects on a slope. this is 37 degrees. This is our block. This is our mg. So normal force, frictionless, so will not include friction. Component of the weight down the slope, mg sine 37. Component of the force perpendicular. Interesting perpendicular line. This looks better. Mg cos of 37. So I've just tried to show the forces that are on this system. So here we have a spring, which has got a constant K is equals to 200 Newton per meter. What else are we given? Newton per meter. I hope that's clear. What else are we given? Alright, so the extension of this, compression delta x is going to be equals to 0.20 meter. Okay, in a known distance from the incline point of release, there is a spring. It is observed that the mass is brought to rest after compressing. Okay, so which means it's going to move from this to probably this point. This is our D. And this is our delta x. Okay, that's our delta x. That's our delta x. This is our delta x, which is equals to 0.0.20 meters. Because it's going to stop after compressing. It's going to stop after compressing that spring by a distance of 0.2 meters. Alright, so again, we have a frictionless surface, so we're dealing with the conservative forces. So again, we have energy that is being converted from one form to another. We have what do we have there? We have the work that we have got the work of the energy that the slope has. So the energy, not the slope, the block, right, as it is sliding down, it has got some energy that it possesses, right? So there is going to be work done in moving that block from its starting position, you can say X, until it reaches to that point Y, right? So the energy required to stop this block is the energy equal and opposite to the energy that this block possesses, right? And this is the energy that is being exerted onto what, or dissipated as a result of the what, of the spring, which is going to be used to load that spring. Okay, so we have can say kinetic energy being converted into elastic potential energy, the kinetic energy of that block being converted into elastic potential energy in the spring, right? But we have nothing that we could use to calculate the speed of that block, right? So we can actually calculate the work done in moving this block from point X to point Y after it has traveled a distance d, right? And we know that the work done is equals to force times the distance moved by the object, right? And we're saying this work is going to be equal to the elastic potential energy of the spring, which is going to be stored by the spring as a result in bringing this block to rest. And we've used the equation before. It's a half k delta x squared, right? And what is the force? It is the component of the weight down the slope, because we are told that it was initially at rest. It's on a frictionless incline, right? Which means that it's going to move down the incline as a result of its weight, and we've identified the component of the weight down the slope. So it's going to be mg sine 37 multiplied by the distance d, which is equals to half k delta x squared. And our mass is 1 g 9.81 sine 37 times the unknown distance d, which is going to be traveled from point X to point Y. Alright, actually my point X should be here, right? Oh, it's just the same, depends where it's going to end. So, however, it doesn't matter. If you assume it to be a point mass, easier. Half k is 200 times delta x, the compression. We're told it stops after compressing the spring a distance of 0.20. So to get d, d is going to be equals to half of 200 is 100 times 0.20 over 9.81 sine 37. So we can punch this. Nine 9.81, we get oh, I forgot to square that value. So this is squared, this is squared. Correct that. That should be 100. That's 0.68. 0.68 meters. That is our D. Alright, so that is how we find that D there in that case. That is how we find that D in that case. My calculator has disappeared. Okay. Alright, so principle of conservation of energy at play there. Yes, moving on to the last question for the day. It says a mass, okay, the question reads, a mass of 3 kg is dropped from the edge of a 50-meter tall building with an initial speed of 0. The mass strikes the ground with a downward velocity of 25 meters per second. Find the average change in mechanical energy of the mass caused by air resistance between the point where it is dropped and the point where it strikes the ground. So you can put a sketch there. This is our building, 50 meters tall. That should be a skyscraper, right? Right, so this is our mass of 3 kgs. What are we told? The mass, okay, initial, so U is equals to 0, V is equals to 25 meters per second. So we want to find the mechanical energy caused by air resistance. So in this case, we now have a concept of a non-conservative force, which is air resistance, which we're told that it is in play, right? So what equation do we know? What equation do we know for a non-conservative force? We know that the equation for a non-conservative force, it's the final mechanical energy minus the initial mechanical energy, because we are looking for the energy dissipated as friction, and the energy dissipated as friction, that will be our enclosed our work done minus the, which is equals to the final mechanical energy minus the initial mechanical energy. And what is our final mechanical energy? Our final mechanical energy, we are at this point, right? And our initial, we are at this point. So we are going to find the change, right? So I'm going to put this W and close this equals to. So our final will be having our kinetic energy, which is a half mv final squared plus our potential energy, which is our mgh, right, for our final minus the initial, which is half mv. Okay, we can use mu, half mu squared plus mgh, right? So this is our height initial and this is our final, right? And our final position, this is our final position here, H is going to be equals to a 0. So which means this term is going to go, which is going to be equals to half mv final squared minus, this term is the initial, and we're told that u is equals to a 0. So this term will go, so this is going to be plus 0 minus 0 plus mgh initial. And our mgh initial, the height there is 50. So substituting, that is going to be half. The mass is 3 times 25. The final speed squared. Okay, this should be like this. And this becomes minus 3.981 times 50. Alright, so what's left is punching. What's left is punching. That is our equation for the work done by non-conservative forces, right? It's equals to the final mechanical energy minus initial mechanical energy. And you know that mechanical energy E, we are looking at the kinetic energy plus your potential energy, right? You should be familiar with this equation. All right, so punching that, so half of okay, minus 3 times what is happening? Why am I not getting an answer? Why am I not getting an answer? Is this the correct answer? I don't see a 0.68 there. Is it my punching which is okay? Why am I not getting an answer to this? Okay, 3.3 times 9.8 times 50. 3 mgh 9.81. Okay, 0.532. Okay. Okay, this is 532.5 joules. And this has been given in kilos, so divide that by 1,000, we should get negative 0.53 joules, or kilojoules, we've put a prefix there. Alright, so that's how we've worked that question out. We looked at the concept, we realized that there is a non-conservative force, which is in this case air resistance. So this is the amount of energy that is dissipated as a result of air resistance. Okay, so always remember you have to check whether this is a non-conservative force or it's a conservative force. In this case it was a non-conservative force, and we had to use the equation of finding the difference in mechanical energy, final mechanical energy minus the initial mechanical energy. I guess this is what I had for you guys. Let me know if you've got any questions. I don't see any questions on the chat box. Alright, if there are no questions, this is what we had for you guys for the tutorial on Thursday. I hope we'll catch up again on another tutorial session. Be sure to join in again tomorrow, the Friday session, to conclude the topics on work energy. Otherwise, from me and everyone in the studio, it's a goodbye. We wish you the best in your studies. Please do make use of the tutorial sessions. If you've got any questions, let your tutors know so that they can assist you. Alright, cheers.